It's not going to let me record today. So the place where the tangent line touches the circle is called the point of tangency. So theorem 9.1 has to do with a tangent line perpendicular to a radius. It says if a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. All right, so remember the arrow means if then. So if this, then that. So on the if, and then remember that the name of a line can either be two capital letters of points, or it can be an italicized letter that's at the end of the line, like either side. So this is an italicized M. So if line, and it is lowercase m, we should just use cursive for italics. If line M is tangent at point capital T, then this is what you get. If I draw a line from T to the center of the circle, that is going to be perpendicular. So then segment OT is perpendicular to line M. And of course, O to T is lowercase r, radius of the circle. So the nice thing about that is it gives us all kinds of right triangles, because if you fill in the other two sides of the right triangles, you've got a lot of math you can do with that. So that one's really liberal in what you can do. All right, let's go on to theorem 9.2. If a line in the plane of a circle, so in the plane means flat, is perpendicular to a radius at its outer end point, then the line is tangent to the circle. So this is basically the reverse of 9.1. In this one, you start with a radius perpendicular to a line that touches the same point. So in this one, the if, what you start with, if line, and that should be a cursive L, if line L is perpendicular to radius RQ, if line L is perpendicular to radius RQ, then line L is tangent to circle Q at point R. And that is your point of tangency. So these go in reverse order. If you have a tangent line, then it is perpendicular to the radius at the point of tangency. If you have a line that's perpendicular to the radius at the point of tangency, it's a tangent line. So it goes both ways. All right, so let's look at this example. Given circle C with line TF tangent at point T. Okay, so right away you go, tangent. That means this is a right angle. And then they tell you TC is 4, so let's label that, 4 centimeters. FC is 5, let's label that, 5 centimeters. Find the length of TF. And we're just going to label that X. Okay, so this little triangle right here is a right triangle, which means we can use the Pythagorean theorem, which of course is a squared plus b squared equals c squared, where c is always the hypotenuse, or the side opposite the 90. So filling in my numbers, my legs are 4 and x, so we're going to go 4 squared plus x squared equals, and the side opposite the 90 is the 5, so 5 squared. And we're going to solve for x. So 4 times 4 is 16, plus x squared equals, 5 times 5 is 25. If I subtract 16 over to the right, I get x squared equals 9. This is the move everybody forgets to do. To get an x out of an x squared, you have to take a square root of both sides. Two x's, one comes out, it's plus and minus. 9 is 3 times 3, so 2 3's, one comes out. We can't have negative length, so I just keep the positive 3 and ignore the negative 1. So yes, points of tangency come with lots of really cool right triangles and things that you can do Pythagorean theorem with. All right, flip the page. No, absolute value means plus and minus. So on this, that doesn't make sense because you can't have a minus. You can't have a negative length. But you're right, normally it would be. Yeah. Okay, corollary. Here we go, corollary. Two lines are tangent to the same circle, and they intersect at a point outside of that circle. Then the distances from points of tangency to the point of intersection are equal. Now, this sounds really complicated. It's really not that big of a deal. So I have line AC, and it is tangent at point B. I also have line AE, which is tangent at point D. And the two lines meet up right here. They meet up outside the triangle. So that's your setup. Two tangents that meet up outside the triangle. So what this is saying is the distance from the point of tangency to the point of intersection are equal, which means B to A and A to D are equal to each other. So AB equals AD. Now, what is useful about this is you now know that if you draw a line from the center to the point of tangency, it's perpendicular. So from Q to D and Q to B, you have a perpendicular angle. If you draw a line from A to Q and BQ and QD are radii, so they're the same, I have a side that's congruent, an angle, which is 90, and a side. So by side, angle, side, I now have triangle ABQ congruent to triangle ADQ. And I can do all kinds of stuff with CPCTC after that. So when you have two tangent lines that meet up on the outside, this creates this really unique double triangle situation. And then anything goes for right triangles. Pythagorean theorem, trig functions, it's all the world is your oyster. And that you will do on your homework multiple times. All right, special tangent vocabulary. Here we go. Common tangent. A common tangent, there are actually two types. There's a common tangent, there's a common internal tangent, and a common external tangent. Those are the two types that we have. But in the basics, a common tangent is a line that is tangent to two circles at the same time. So if you draw a line that just touches both circles at one point, that is a common tangent because it's tangent to both. The common tangent can be a line or a segment as long as it's tangent to both circles. And then put segment, put or array. It can also be array. As long as it's a straight function and it touches at two tangent points, you're good. The circles must be coplanar or in the same plane. So the circles have to be flat. They cannot be as like a sphere. It's got to be flat here. In a plane means flat. All right, so common internal tangent is a line that is tangent to two circles. It is a line that also crosses the segment joining the two circles. So this one always gets people. So it's tangent here, it's tangent there. And it crosses inside the two circles. So the line crosses the segment joining the two circles, which is this segment right here. So that's a common internal tangent, is if it crosses the line joining the centers. Okay, common external tangent is a line tangent to two circles. This line does not intersect the segment joining the two centers. So in this case, a common external tangent is outside of the two circles, and it does not cross the line joining the centers. So common internal tangent, common external tangent. Okay, flip the page. Okay, externally tangent circles are two circles that are tangent to the same line at the same point. That's externally tangent circles. Neither circle overlaps the other, and the circles are coplanar, they're flat. So your tangent line basically is squished in between the circles and only touches them both at one point. It just so happens that one point is shared. So externally tangent circles. Okay, number 5, internally tangent circles. Two circles that are tangent to the same line at the same point. So that's the same between the two. The circles are coplanar, so flat. That's also the same. Here's where it's different. One circle is inside the other. In other words, we say that their spaces, that's the geometric word for that, their spaces overlap. So it means that there's another, and I really can't freehand circles, but there's another circle here that also shares the same point of tangency. That's an internally tangent circles. They're internal inside each other. All right, let's do some practice. Number 1, name all segments that are congruent. Okay, the easy two would be the radius here and here. So that's the easy ones. So segment TC is congruent to segment RC. So that one's easy. But using our new theorem, we have two tangents that meet up at P outside the circle. So from P to the point of tangency is the same length. So PR and PT are the same. That's using our new theorem. Okay, let's look at number 2. Complete the sentences about circle N and trapezoid ABCD. Circle N is inscribed in trapezoid ABCD. Trapezoid ABCD, we say, is circumscribed about circle N. So when it comes to circles and they're being inscribed in a figure, it means the circle is as big as it possibly can go. If a circle is as big as it possibly can go, it's going to be touching at multiple places. So when you're talking inscribed circles, it's got to be as big as the thing can get. Okay, so now we're looking at this little lovely. It says, name all common interior tangents of A and C. Okay, so common interior means it's two tangents that cross the line that joins their center. So here we go, joining their centers, AC. So we want two tangents that cross that line. So that would be this one right here, that tangent, and it would be that tangent. So that would be JI and GH. Okay, name all common exterior tangents. Common exterior tangents are tangent, but don't cross the line between the centers. So I have one common exterior tangent there, and I have one common exterior tangent there. So that would be BD and FE. All right, complete the sentences. Segment JP is congruent to what? Okay, so you got to find JP. JP is from here to here. That's JP. From a point of tangency to an intersection outside the circle. So J to P and G to P have to be the same length by our theorem. So JP congruent to GP. Put the bars on it. It's a congruency statement. Okay, same thing here. P to H, H is your tangent. P is where the two tangents meet up. So P to H is congruent to P to I because you have two tangents meeting up outside the circle. All right, FE, which is this blue line right here, FE is tangent to circle A at, it's tangent to it right there. It's at point F. That's its point of tangency, where it touches it. Then it says point D, which is this one over here. Point D is the point of tangency of two different things. So obviously it's tangent to the circle. And then, but also it's the point of tangency of this segment BD. It's the point of tangency between BD and the circle. So line BD would be the other structure that it's a point of tangency. So point of tangency is for circles and lines. All right, last one, JP plus PL. So JP is this one, PL is that one. So using what we know about congruent segments outside a triangle, JP and JI, wait, JP plus, oh, sorry, wrong one. JP plus PL, yeah. So 2 plus 1 equals, okay, so BP is the same as JP plus PH is the same as PL. So J to I, tangency to tangency, is equal to B to H, tangency to tangency, because 2 tick marks plus 1 equals 2 tick marks plus 1. Oh, G, not B, G. Sorry. I tried to make the drawing bigger, but it didn't have enough pixels. It just got harder to read. Yes?
On
Oh, that's supposed to be a G.
Where is I on the drawing?
On the drawing's right there.
And then where's L? You said L. Oh. I don't know, you must be back and forth from I to L.
I haven't used it.
You just said L.
Oh, yeah, it's the same thing. The I, this is an I. It's just the font that they use. It's supposed to be a capital letter, and it doesn't look like a capital L or a capital I. So yes, that is frustrating. I agree.